Apology to interrupt. My sound is down. Can anybody else also hear, or is your sound also off? Yeah.
Apologies. Can you hear me now?
Yes, thank you. I can.
Thank you.
Okay, should we do a radio check, everybody?
Everybody happy? Can you hear? Okay. Apologies.
Oh, so it looks like there's some thumbs up.
Okay.
Perfect. It's nice to see my dad is actually in the meeting online. In fact, there's a photo of him coming up. So that's really great. Okay, so this is some work I did for Acton last year, and we have a history between Acton and WITS where we do some torque speed measurements for their large machines. And what's important really is our work as a university is just a verification role. Acton have built this machine for a customer. The customer wants it verified that what it's claimed to do, it does before the large cost of moving it off to site. So our role is a third-party verification role in this. I've made this as a paper for the South African University's Power Engineering Conference that we spoke a bit about briefly earlier. As you can see, I'm not a student, so I don't really qualify for the student prize, I'm afraid. But nonetheless, I thought it would be quite interesting because we've done something interesting here, and I thought I'd share it to you today. So here we are. Okay, so what we're going to do is determine an induction machine's torque speed curve, and all of you are very familiar with why torque speed curve is so important, particularly for induction machine. How we're going to do it is different. We're going to do it using an audio spectrogram. So from the sound that the machine produces, and I'll explain to you why we did it that way this time. And obviously the test is done during run-up. So in fact, we plug the machine. So we do the test from full speed reverse to full speed forwards, take some speed measurements, work out the acceleration, derive the torque, and do some other scaling. And then we have this torque speed curve, which generally matches up with the designed curve, obviously. Okay. And well, we haven't had any problems, but we've always found some interesting things which I'll share with you.
James, can I make a suggestion? Try to view full screen. Okay, we can come back to full screen.
Yeah, control L.
You should come down to here. Extract it.
Okay, great. Thank you.
It's really big. Okay, just the overview of the presentation very briefly. I think I've given you an introduction already. We'll look at the background, how it's traditionally done, and the motivation and objectives. So what are we doing? Why are we doing this work? The experimental procedure on the work that I've carried out at Acton, and then the analysis of the data. The interesting part is in the curve fitting. This is where the academic part comes in, and the modeling and the curve fitting there. We'll talk about some results, some recommendations, and we'll conclude. Okay, so as I've said already, induction machines being asynchronous, the torque is proportional to the slip. We'll look at that briefly in some various torque speed curves in a moment. And it's primarily dependent on the rotor circuit, as you all know. The rotor circuit is what shapes the torque speed curve, so single cage, double cage, etc. And that is done to satisfy various industrial loads which require these different torque speed curves out there. So, for example, fans and pumps, we want a square law torque speed curve, or a mill drive, for example, where we want relatively constant torque. We can achieve those with in our motor design, primarily from the design of the rotor circuit. Okay. And I'm involved here by doing verification work. So taking measurements, seeing how they compare with the design before the motor moves to site. Obviously, it's very expensive to move it there, find there's a problem, and then move it back for repair. You don't want to do that. Okay. All right, so this is an example from a test many years ago. It's a 10 megawatt machine, 750 RPM, single cage rotor, and you can see this absolutely classic torque speed curve. Very, very high put-out torque, in fact, 5 times the operator value. There's an operator value about 0.6 per unit, and here it's peaking at about 2.8 or something. So very, very high put-out torque. Classic single cage rotor design with very shallow bars. In terms of the relationship between curve and slip, you can see here there's a very clear 1/S function. on this range of the slip from 0 to 1, so 1 over S function. And on the right-hand side, after the pull-out torque, we have a proportional to S function, so almost linear straight down, basically to 0. And typically the load, in this case, would be a pump or a fan, would have a square door which would sort of intersect over here. Operating point is over there. So that's a classic single cage machine. Okay, here's mine. Dad stand in front of the machine, and you can see an enormous machine. So we want to do the tests on the factory floor before it comes out. So being able to do the test then and there is quite important. You can't put this onto a test bed and measure the reaction torque, etc. It's not possible. Okay, this is another machine, but smaller, 1 megawatt, just over 4 volt. Then you can see again, classic single cage design. What's interesting in all these torque speed curves is the shape comprises 2 components. We have a shadow bar which produces this very curved 1 over S function, and then we have, adding resistance into the bars, we have another curve going this way. So we're going to see these 2 curves. We can shape these curves depending on the rotor circuit, design of the rotor circuit to achieve the torque speed curve that we want. Okay, you can see it's a bit of a trade-off. As we bring in torque here, we lose torque over here. In this case, the pull-out torque is only 3 times the lock rotor torque, sorry. So pull-out torque about 2.5, it's about 1 per unit of lock rotor torque. Okay. Right, in the next case, this is a classic mill drive torque speed curve, and always the double cage design. So here you can see the deeper cage contribution is dominating, and the original shallow cage, you can still see that impact. There's another curve over there. So here you can see the pull-out torque is actually less than the lock rotor torque, about 0.8. So that's a classic mill drive. And you can see very high torque values across the full speed range, which is what you want for a mill drive. Okay, so how do we do these torque speed tests? We do it at a reduced voltage, first of all, to avoid saturation effects. We don't want the current to go over the rated current, otherwise the machine saturates and then you get very inaccurate results. And when I say reduced voltage, it's typically like 0.3 per unit, 0.4 per unit, so very, very low. This has an advantage for us because it extends the run-up time. So instead of a direct online start taking seconds or milliseconds, by doing it at a reduced voltage, especially very low, we have a very extended run-up time, maybe over a minute. So we can really take lots of data samples in a minute as that machine accelerates. So that's quite helpful for us. It becomes a bit of a trade-off because you need the voltage low enough so the machine doesn't saturate, but it has to be high enough that it can produce enough torque to overcome stiction, otherwise it doesn't accelerate at all. And also sometimes it gets stuck at a harmonic torque or something where it doesn't quite accelerate to full speed, it sort of just gets stuck at a certain speed. So the voltage has to be low enough, but also has to be high enough to get it to accelerate to full speed. And it's done under no load, so normally completely uncoupled mechanically from the load, and it's effectively just accelerating its own inertia. Right, so what we do is we accelerate the machine to full speed in the reverse direction. Then we plug it by reversing 2 phases, which causes the machine to run through the braking region on the torque speed curve. So the machine decelerates quite quickly. It goes to standstill for a moment, and then it accelerates in a forwards direction to full speed. So the test is done from full speed reverse to full speed forwards, and we achieve this by plugging. So reversing 2 phases, and that brings a slip of 2 to the circuit, so into the braking region on the torque speed curve. Right, so I've got a picture here of holding a handheld tacker. We don't do it this way. We use a small tacker generator to produce a signal. The reason why I put the photo in here is it's critical. One of the problems of doing it with a handheld device is that it's almost impossible to get the tachometer in line with the shaft. And especially when you're using a 10 megawatt machine, the shaft's like this, and normally we take some varsity students to do it. Very intimidating, this whole thing. it's rotating in their face, and that fan is blowing full air into their face, and they're trying to hold this thing shivering normally from fear. But the bigger problem is it's very difficult to get into line, so it starts to wobble like this. And as you know, if you have a wobble or a vibration in the speed trace, as soon as you differentiate it to try and get an acceleration, that is completely amplified, and often it drives out the torque speed curve itself. So the alignment of doing this actually is critical to get a nice smooth trace. That's part of the reason for doing it with the audio signal, what I've done here. Okay, so how do we do the test on site? Well, we measure a speed versus time trace using a tacho generator, as I said, normally handheld, quite small. And we produce two signals from it. The one signal is this effectively voltage versus time, which is directly proportional to the speed. And then we use an op-amp circuit to differentiate it, which will then produce a real-time acceleration versus time trace. And we put both of those channels into a recording oscilloscope, which we can then download later. So we're using a tacho generator to produce a speed signal. We're differentiating it immediately with the op-amp circuit to produce an acceleration signal. And what's also important, if the voltage remains constant, then we've got a pretty good relationship between the torque and the acceleration. But what we found is that for larger machines, because they're being tested only by a generator which doesn't have Ethernet bus bars, the voltage regulation is quite difficult. And as you know, the torque being proportional to the voltage squared, any fluctuation in the voltage has a significant effect on the torque. So for the larger machines, we actually measure the voltage as well. Record it all on the storage oscilloscope. And then when we get back to the university, we then do some processing. We scale our measurements by the voltage squared. It's very important to keep the voltage constant. And then plot the acceleration versus speed. And then we scale it by the locked rotor torque value, which is at 0 speed, obviously. And that's normally provided by the manufacturer. What's very important here is the voltage has a significant effect on the results. So the voltage must be kept constant in these tests, or you must measure it and be able to fix it later. The other important thing to note is that the locked rotor torque is obviously at standstill. So as the machine is decelerating, it's stationary for a moment and then it accelerates. We need to know what the torque is at that point so that we can scale it by the locked rotor torque value. That's also critical. And in fact, that's going to become quite problematic later in the presentation. Okay, so just to continue, so we use our handheld tachometer. The scales are a bit small here, I apologize. The y-axis is the speed in per unit from standstill to full speed. And the x-axis, in this case, it's the number of samples, but you can think of that as time. And in fact, for this particular machine, I think the run-out time is about 50 seconds from the x-axis. The x-axis from the left to the right is about 50 seconds. I can't remember exactly what the rated speed of this machine was, but I think you can all immediately see that it's pretty straight. The line is pretty straight. Up to this point, up to about, let's say, I've said a sample 2000, which is over here. So here you can see that the line is really starting to climb. So the speed is accelerating constantly, and then it really climbs very steep. The gradient of the line is climbing very steep in this top right corner. So that's obviously where the machine is approaching its pull-out torque. And we can see just from this results already, you can see this very steep gradient above sample 2000 has it's evidence of a very high pull-out torque. Okay. And if I stand and look up the curve like this, I can see there's one point of inflection over here. So there's a negative gradient here, a positive gradient over here, negative gradient, and then a positive, very steep positive gradient to the top. And then right at the top, there's another point of inflection. So this curve, we're expecting 5 clear regions, is what I'm trying to say. If I look at the curve like this, it's probably not so obvious for you when you're looking that way. Anyway, if we take that and we differentiate it, so we're looking at the gradients now. How does the gradient change? You can see it's relatively constant up into about the sample point 2000, and then it climbs very high towards the pull-up torque. So there's huge acceleration towards the end. And you can see there's more or less 5 regions. So there's a negative over here, positive, negative, positive, etc. So there's 5 clear regions. Okay. Just a note I've made here, the pull-up torque shape is influenced by the nonlinear speed versus time. So in the previous graph, we see this very steep climb here, right at the end, towards the end. And you can see that's resulted in this very rapid increase in torque. In fact, here the pull-up torque is roughly 2 times the lock-rated torque. So lock-rated torque is about 0.5. Pull-up torque is, I've just called it 1 in this example. And then if we look at the voltage, so this is the voltage recorded during the same test, relatively constant. Now, just to give you some background, that's controlled by a test bed operator who's got this big synchronous generator next to it, and he's controlling the field winding on that synchronous generator. And obviously, as the machine runs from just after it's been plugged, where the slip is 2 massive currents going into the machine to break it, you can see that the voltage is quite difficult to regulate. It's going up and down, and he's doing his best to regulate that voltage. And then towards the end, as the machine then starts accelerating, the current reduces quite significantly, and you can see the voltage comes up to full rated value. So just to give you an idea how sensitive it is, so in this case, if we assume, take a straight line across there, which is about 0.85, maybe 0.9, straight line. If we then square that to work out the torque, that results in a 25% increase. So just going from 0.9 volts, 0.9 per unit to 1 per unit changes the torque value by 25%. Okay, so it's extremely sensitive to that voltage. So it's critical that A, the voltage remains constant, or B, that you at least measure it so that you can correct it at a later stage. Okay, and then just to finish off with that machine, in this example, you can see there's the final torque speed curve. So the resultant pull-out torque is just over 2.5 compared to 1 per unit at the lock-rated value. So you can see how the voltage measurement has done 2 things. It has changed the peak value here, but it has also changed the shape. This is the acceleration versus time graph. You can see it's very, very narrow, this pull-out torque here, but when you actually scale it at the voltage, it looks more like what we're expecting. You can see this machine's got a single cage rotor shadow bars, so that's producing the 1 component curve, and you can see there's either the bar, it's not quite on the surface, or there's some resistance in it. You can see the other curve contributing a little bit. And then this feature, we'll talk a little bit later about it. Harmonic torque's very problematic. But this machine, you can see there's evidence of 1, but it has no effect on the load, which is probably squared or 3x. So it's no impact. Okay. All right. So that's a background how we do it and why we do it. And now we needed a new method. And the reasons being, Acton needed us to test a 0.5 megawatt 2-pole machine, pump drive. So relatively small, very fast. 2 poles, 3 poles. Yeah. 2 poles, sorry, my 1500 is correct. Yeah, sorry. That 1500 is correct. What's 3000? 3000 machine, 3000 RPM. Okay, so the equipment that we needed so far, we had to have a handheld tacker generator, some op-amp differentiator circuit, the power supply for that, all the cabling, and then our storage oscilloscope. The equipment becomes quite unportable, and it actually needed several people to help you. One to do the voltage measurement, one to hold the tacker, one to do the readings on the scope, and another one just to manage the whole thing. And it becomes quite fiddly, especially with the tacker generator being held against the shaft, and particularly on the large machines. Not only is that shaft spinning at a very intimidating 3000 RPM at this machine, but also it's floating backwards and forwards through the bearing. So it's actually quite a task to do it. The real reason why we needed a new method is all the stuff during COVID had been locked away in a storeroom and we couldn't find it. But that's the real method. That's typical university. So we needed a new method. Okay. A contributing factor is that during the differentiation via hardware is quite problematic because it's very sensitive to the environment, as I said already, to any kind of vibration. So if the machine's vibrating on the test bed or the test bed itself is vibrating, it becomes quite difficult, and you have to employ quite a significant smoothing process to pull out all that artificial noise and focus on the measurement on the rates that you've actually recorded. Now, this technique that I've presented to you up to here, I refer to it as a traditional method. It's about 90 years old. In fact, there's some papers going back to the 1930s where they describe this process and how they did it, because they didn't have a storage scope in those days, is they used a CRT display and they put the tacho generator output onto the y-axis, and the differentiation onto the y-axis, tacho gen on the x-axis, and it gives you the torque speed curve immediately. So that was the thinking 90 years ago, and we're still doing it the same way. So that was very good work by the engineers in those days. After lots of thought and considering what can we do with our cell phones, it's actually quite surprising how many apps you can get on here for engineering related stuff. I was going to tell you later, but I'll tell you now, there's an ammeter app on here. An ammeter, you can measure RMS current, DC currents. What it does is it measures the magnetic field passing through the phone, which is quite nice, and you calibrate it by some fixed distance. Now that's a brilliant engineering app. So I thought, well, surely we could use this to something in this application. There's a lot of vibration analysis apps as well. So my original thought was, well, if we can measure the vibration of the machine, because the vibration is synchronous to the speed, then we can work out the rotor speed from the vibration analysis. I did quite a lot of testing, but I wasn't really satisfied with the results. Otherwise, it wasn't good. Well, certainly not on the free apps. So what I did in the end, what worked very well was recording the audio sound. It turns out that the major element of the sound produced by the machine is from the impeller. And what we're going to look at later is the frequencies of the harmonics produced are related to the number of impeller blades, directly related. So it's an integer multiple, which makes it very easy. So if you can measure the sound from your phone with a spectrogram, you can relate it to the speed directly by the number of impeller blades, which we'll look at that. So that made it quite. I also looked at some kind of pulse counting technique where you could, so some kind of stroboscope where you could record, a point going round and round. But what's quite a common problem from all these techniques is determining when does a shaft stop and change direction. Because if I'm taking a pulse and it's slowing down and it stops, I don't know where it stops, where the next pulse goes, because it could start rotating and then the pulse goes. So I don't know where the changeover is in the direction. And as I alluded to earlier, it's critical to know when the machine stops so that you can scale it correctly by the lock rotor torque. So that option was ruled out. So we went for the audio spectrogram, and we'll talk about that in a moment. Okay, so just very briefly, what is a spectrogram? Well, it's a three-dimensional plot. I'm sure you've used all of them all of you in your industries have used it before or have some knowledge of it. It's a plot of frequency and intensity versus time. Time is generally on the x-axis, frequency on the y-axis, and intensity is related by color. So it's a three-dimensional plot, effectively. In this case, how I did it, I used this app called Spectroid. It's really fantastic if you've got kids or friends at varsity who you're battling with signals and understanding that kind of stuff. This app is really fantastic, and you can play around with audio signals, and it will give you a very nice breakdown of it. Best part is it's free, and it plots a real-time FFT on the top here. So we have intensity, I think, whereas frequency on the top, and then it has this recording function, which the axes are shifted. I'm going to decode it in a moment, but it records the FFT versus time, which is what we want. And I've just made a note here. In this case, it scrolls vertically, so the news date is at the bottom, and it scrolls that way, which is unusual. But if we turn it around in the next slide, we can have a look what's happening. Okay. So I did some preliminary testing in the lab at Wits, small machine, also a small active machine, 3 kilowatts, 4.25 revolutions per second, at a reduced voltage, 60 volts. So that's quite easy. We just set the voltage of the transformer 60 volts, so we know the voltage is constant. And just to give you an idea, this run-up time, so from full speed backwards to full speed forwards is about 10 seconds. Okay. Let me just show you some features on the picture here. On the y-axis here, we have frequency, and you can see there's 5 distinct lines. 1, 2, 3, 4, 5, and you can see the traces over there. So those are harmonics related to, in this case, the 5 impeller blades. So 5 impeller blades, if the machine is turning at 25 revolutions per second, we're going to get harmonics, integer multiples of the speed. So we're going to get a first harmonic at 25 hertz. In fact, let me use this axis here because there's the units: 25 hertz, 50 hertz, 75 hertz, 100 hertz, 125 hertz. So those harmonics are being produced by the sound of the machine, directly related to the number of impeller blades. Okay. Just to give you an idea, the colors tell you the loudness. So the brighter the color, the louder that harmonic is, or the louder that sound, the more prominent it is. And obviously the darker, the quieter. So dark is very quiet. I'll try and emulate the sound of this machine. So the machine is running full speed backwards, first of all, so running at full speed. We try it again. Then what we do, we disconnect the phases, we reverse 2 phases, re-energize. So the machine coasts for a moment whilst we're fiddling around with cables, so it's slowing down. And then when we re-energize it, it goes into a braking region, and you can see it decelerates very quickly. So here it's coasting, and here it's decelerating very quickly to standstill, basically. I'll do the sound again. And then it accelerates in the other direction. Okay. You can see the braking region is actually very short here, very short duration. You can see the acceleration time is quite long. So here, as I showed to you right in the beginning, this emulates a speed versus time trace, and you can see the gradient, which is acceleration. You can see it accelerates quite quickly in the beginning, slows down a bit, and then here, as we reach a pull-up torque, you can see the gradient is climbing very steep. So this is typical. Just by looking at this, you can see it's already a single cage machine. Once again, I just want to reiterate, because there are 5 impeller blades, there's a relation of 5 times the machine speed. So we're going to get harmonics at 25 hertz spaces, 25, 50, 100, 125 hertz. And you can see the split harmonic is the clearest out of all of the others. So the clearest audio waveform. And that basically represents our speed versus time trace very clearly. Okay, just to show you something else, you can see where the machine stopped was quite problematic. There's almost no signal, no sound being produced by the machine. Obviously, it's not rotating anymore. And what I resorted to in the end was, you can see there's a very faint vertical line, basically the whole way up, is I could watch the machine. As the machine stopped, I could just tap my recording device with a pen and to say, right, that's where it stopped. And you can see there, that's where I tapped. I tapped my phone, actually, the phone recorded an impulse when I tapped it. So I know that the 0 speed point is down here. And you can sort of see that's where it converges. If you follow this line backwards, that's where it converges down there. Okay. And last comment here, intensity and frequency proportional to speed. You can see the faster the machine is running, obviously the louder the sound. So it's very clear. I can hear exactly what speed it's running at. When it's running at full speed, obviously at lower speeds, it's a bit more difficult. So they're related to the speed. Okay, so I walked out of Wits with great confidence in this method. This is going to be easy. Because there it is, it's clear as day. There's the speed trace. I just have to record this, and yeah, I'll be back within an hour. Okay, here's the machine on the test bed. What I found also from some experimentation is that the fan shroud is a very good emitter of sound. So this big surface that's vibrating away, you can't really measure anywhere on the cooling fins, obviously, because the air is blowing over it, and you just have white noise which drowns everything out. So you have to stay out of the airflow to take your audio recording. And the actual factory is extremely noisy. So the background noise levels are very, very high. And a giveaway I should have known is that when I walked into the factory, everybody's wearing earplugs. And then I should have noticed, oh, we might have a problem here. Okay. What I found to get rid of the background noise is that if I could conduct the sound through my finger, through the bone of my finger, by squeezing my finger so it's solid, I could conduct the sound energy out of the shroud straight into the phone's microphone without it picking up the background noise. So it's measuring the sound conducted through a solid into the machine as opposed to coming through the air with everything else. And that helps quite a lot. Obviously, as I've said, out of the airflow, because the wedge noise is what we call white noise. It's just all frequencies and it just drowns everything. The fundamental problem I had here is that this position at the back of the shaft is I couldn't see the front of the shaft, the rotating end. So I didn't know when the shaft started. And that was quite problematic in this machine because the run-up test was done over a minute, maybe even 2 minutes. And it slows down so slowly, it goes completely quiet, it slows down completely that you don't know that it's turning anymore. You can't feel any vibrations. There's so much background noise in the factory. You don't know when the machine is actually stopped, which in hindsight, it would have been better if I maybe tried to at least peer around the corner to see what was happening on the shaft end. And it was covered by a protection shield anyway, so it was very difficult. And basically all of these made the whole experimental process very challenging. And that's why we turned it into a huge academic exercise, which we're going to look at now. Okay, so this is the audiogram that I got, which if you compare it to that one, this is easy. Compare it to this one, this is vastly different. Okay. So once again, this is a 2-pole machine, 50 revolutions per second. So we're going to expect harmonics at 50 hertz intervals. Just out of interest, this machine had 12 impeller blades. So I'm walking into the factory expecting I want to measure a 600 hertz harmonic. So 12 times 50 giving me the 600 hertz. What I found after lots of tests, what I actually found quite well is that the lower order harmonics works very well. So this is a first harmonic at 50 hertz, second at 100 hertz, third at 150, fourth at 200. And there was no need to measure the higher harmonic. So this 600 hertz, it wasn't necessary to measure. Okay, after quite a few tests on the test bed, we managed to convince ourselves, between myself and the test bed operator, that the supply voltage, we could keep it relatively constant. I had no ways of recording it this time. So luckily, this was quite a small machine compared to the test bed generator, which is in the order of megawatts. So we were quite confident that we could keep the voltage constant, which becomes a fundamental assumption later in this work. And the run-up time, so from full speed backwards to full speed forwards, is about 40 seconds. So quite a lot longer than the previous one I showed you. And just to show you what's happening, the machine is running. I'll take this trace here. The machine is running full speed backwards. We disconnect the machine momentarily, so you can see it's starting to coast down. So it's slowing down due to friction and windage losses. The test bed operators managed to reverse the phases, reconnect, and here's the braking torque being produced by the machine, with a slip being close to 2. So lots of braking torque being produced, and you can see the machine decelerates quite quickly down to 0. Then it starts to accelerate. And once again, you can see very straight. And then here you can see the gradient is really climbing at the end as the machine accelerates to the pull-out torque. And then it reaches the top, which is the no-load or the free running speed, etc. Okay. What from an academic point of view, what was very interesting here is that you can see the amount of background noise compared to this environment. So our lab was very quiet, no one was working in it, there were no students. But here we're in this factory environment, you can see the background noise is very, very high. That was the problem. The other major problem, you can see there's this white horizontal line across at 100 hertz. And that 100 hertz is due to the magnetic hum in the factory, in this case, the generator sitting right next to it, which is operating at 50 hertz, and that's causing a magnetostriction relamination to the 100 hertz. So you've got this very loud hum in the factory environment, the 100 hertz. Okay. The major problem here is that there's very little data around the zero speed point. We can see the machine is decelerating, and then you can't hear it anymore because it's been drowned in the factory, in the noise in the factory. So we don't know when the machine is, when it has reached standstill, and as I said to you earlier, that's critical to know so that we can scale it with an operator test. So what I've tried to do is I've tried to tap it with my pen again, which produced this vertical line, so that I knew, okay, that's more or less when it stopped, when I was recording it. Right, I couldn't see it, but I thought, right, it must have stopped by now, so I made a mark here, and that's this vertical line, which actually didn't help me at all, because it turns out that the machine is decelerating so slowly at the end that you really don't know. There's no vibration. You can't hear that it stopped. You can't see it. So it became guesswork. Actually, doing this became meaningless. What was particularly interesting, I've just made a note here, the intensities of the harmonics vary with speed. So here you can see this harmonic is very loud compared to the others. Then this one is very loud compared. As the machine slows down, this harmonic is excited, so that one's loud. Then this harmonic, as the machine slows down more, this harmonic is becoming more prominent. And that's, I'm speculating, but I think it's related to the way the machine is constructed. In the previous machine, it's a cast machine, so a cast machine with a fan shroud. So it's really two components that can vibrate. Whether here it's made up of a case, shroud, box, all kinds of panels, and different panels are vibrating in different modes at different speeds. And so you'll see different harmonics are excited at different times. Although it looks problematic, it wasn't too difficult from a data processing point of view, and I'll show you that in a moment. But I just wanted to show that you can see that different harmonics are excited at different speeds throughout this, which as an extra challenge, it's not too difficult, but it was very interesting, and I think that is from different modes of vibration across the machine. Okay, and that's obviously related to the fabrication. Okay, so what did we do then? I needed to get some data points out of this. So the first thing that I've done is I have cut this spectrogram in half. So this is where the machine is decelerating, so it's turning in the reverse direction up to this point here. And here it's rotating in the forwards direction. So that's going to be the braking torque. This is going to be the accelerating torque. So I've cut it in half, and I've inverted the left half to show a reverse speed. So there's a negative speed, or I've used the unit of frequency, but it's directly proportional to speed. So we've got the reverse speed as the machine is slowing down in the reverse direction, it stops, and then it accelerates in the forwards direction. So to resemble a more classic speed versus time graph that we're accustomed to. Okay, so just to show you, once again, the machine is running full speed backwards. We then disconnect the phases, reverse it, and re-energize it. And in that time, the machine is coasting. So this straight line to here. So the machine is coasting whilst we're plugging it. And then when we re-energize it, it starts to brake. And it decelerates very quickly to standstill momentarily, and then it accelerates in the forwards direction to the free running speed, and then it runs it almost full speed to full speed forwards. You can see I've taken some data points here, which I'll discuss in a moment. What I've put here, this blue line is a best fit curve through the data points. So I've just got these discrete points, which I've taken out of the data, and now I'm trying to do some maths to put a curve through it. And the curve that fits the data points best is the blue curve. And the benefit of doing that is that if I know the equation of this blue curve using some polynomial, I can then simply differentiate it, and I have the acceleration. And it's very clean. There's no noise, no vibration, no alignment issues. It's very simple. So that's the objective, is to determine this curve and then just differentiate it algebraically. Okay. I've showed you already, you can see the gradient at the end is climbing very quickly. So this machine's exhibiting a very high pull-out torque without even knowing the results. You can already see the torque is very high. The difficulty came in here is that in fact, there's no data points around the zero speed point. So my last data point is over here, which I think works out at about 0.2 per unit. Then I've got nothing. And then the machine starts making sufficient noise again. I get data again, basically above 0.2 speed, 0.2 per unit speed in the opposite direction. So effectively, there's 15 seconds of silence in what I argue is the most critical range of operation, because I need to know when is that shaft stationary for the locator torque. But I've got about 15 seconds of factory noise, generator noise, and I don't know what's happening here. So this is where the curve fitting process comes in. Just to explain how I extracted the data points very manually. What I've done is I effectively have taken this picture, zoomed in 1000%, and I could plug a point over here. So we have got nice bright colors. I could choose, right, I want to point over there. And I then wrote some, call it MATLAB code on top, which would then start plotting my curve based on the data that I put there. So if I put the point in the right place, I could see my curve matched the other points. And then it was really a hit and miss process to fit all these, to put in all these data points. The nice thing though is that because the harmonics are related by an integer multiple, so first, second, third, fourth, etc. If I just go back to this point, if I am working, let's say, on this curve quite a lot, you can see this curve basically goes quiet very quickly, and then I've got no more data there. But I can then hop onto this curve and start working on it, and I know that this curve is the third harmonic, and that one is a fourth harmonic. So there's an integer multiple. So basically, I can take data from all of these bright spots, and if I string them all together, I get a relatively good string of curves. So all these data points are integer multiples, and that becomes very convenient. So although it looked like a challenge in the beginning, it actually wasn't too bad in the end. The only challenge was that it was very much manual. Although I think in the future this could be done with some kind of image processing or something like that. Okay, so just to summarize, I've taken these data points from the audiogram that was done manually, and then put a blue curve, which is a best fit polynomial that matches with the data points very nicely. Once I've got that, in fact here I've extracted it, and once I've got that polynomial, I can just differentiate it mathematically, and I have an equation for the acceleration versus time, or acceleration versus speed, and that solves all my old differentiation problems. So that's the major benefit of doing it this way. Just from an academic point of view, there are obviously numerous curves which could fit through all these points. And I'm trying to limit it to the lowest order possibles, which are a third order curve and a fourth order curve. And I am speculating, but I think the order of the curve that fits best is related to the number of rotor circuits. So if you have a single cage rotor, you've got one circuit, so probably a third order function. If you have a double cage machine, you have two parallel rotor circuits. That brings in another order of complexity, and a fourth order curve would fit that data. In fact, I've tried both here, and you can see there's virtually no difference between using a third order and a fourth order polynomial. And I think if you actually go into the details, you'll probably find that the fourth order term of the fourth order polynomial is probably 0, making it a third order polynomial. So it's called a fourth order polynomial here, but it's probably only a third order. And I think that's a subject for future work. But you can see the best fit curve, even if I play around with the orders, fits the data extremely well, which is very nice. So this is starting to give me some faith in what we're doing here. There's approximately 5 points of inflection. There will be one braking in the braking region. There's another one going positive gradient, negative gradient, pretty much straight, with a very steep positive gradient and then a negative gradient. So I was expecting about 5 points of inflection, which looks about right. I found that the lower order splines fit best, and I think that's because they're directly related to the detail of the rotor circuit. And although I have no data around the 0 speed point, data point, you can see I'm pretty confident that although I don't have any data in the middle, that both of these lines go through more or less the same point, and I can use that point with quite good confidence. Okay, so I think I've tried to stress the point. There's a good fit here, good correlation. And last point I've made is that we're only considering the torque producing region. So we're ignoring the coasting section where the machine was slowing down, because the machine is not producing torque at that stage. And we're ignoring the free running section. So once it's accelerated up to full speed, effectively the torque is 0, because it's now running at constant speed. So there's no more acceleration. Okay. If we now take this curve and we plot it against speed and we differentiate it, which we do algebraically, we get the resultant torque speed curve. So the previous graphs that I showed you at the start of the presentation were from 0 per unit speed, looking at the acceleration. This graph is showing the braking region as well. So the machine, this is full speed backwards. After we plug it, we have some braking torque coming down to standstill. This is where the lock rotor torque value would be used. And then you can see the machine is accelerating in the forwards direction to full speed, 1 per unit. Okay. The red curve is a differentiation of the third order function. So that's now a second order function. If we take a third order function differentiated, we get a second order function. And the fourth order curve is obviously this now becomes a third order function. And you can see there's pretty good correlation, except in the region that I'm interested in. Here you can see they're starting to separate slightly. In this area, it's 0 per unit. There's a slight difference. Just to explain what the colored dots mean is when you're making a curve out of compound curves, it's very important that when they join, if you differentiate them, they have to have the same gradient so that when you stitch them back together, they're continuous. Otherwise, you have this very discrete, basically chunky looking waveform. So it's very important that the points where you stitch your curves together have the same gradient when you differentiate them. So that's just indicating where the curves are joined. So if we take this blue curve, for example, this is one curve, and then it's stitched together to another curve to there, and it's stitched together to another curve over here, etc. So we're stitching all these curves together. But that's done to achieve this best fit through the data points. Okay, so we call those splicing points, where we splice the two curves together. Okay, what I wanted to show you was the data points here. You'll see this, I've overlaid the data points. These are not really data points because I didn't measure any torques directly. But if I can just go back to the speed curve. Yeah. My last data point, when I was slowing down here at about -6 seconds, I've got a speed of about, that's -10 revolutions per second. So it's about 0.2 per unit. And then the next data point I have is maybe 14 revolutions per second. So also it's above 0.2 per unit, about 10 seconds later. If I take a straight line and I join this point to that point and I take the gradient of that line, you can see it's going to come through very close to what the best fit curve is. So the gradient of the straight line joining that last point there to the first point whilst it's accelerating is this point over here. Over there. So you can see I've got quite good correlation just by taking the 2 points and saying, right, it must be in the middle somewhere. I'm getting very good correlation with what my model has given. So we have some pretty good faith in this. Once again, you can see typical single cage machine, very, very high put-out torque. This, as I said to you earlier, we've managed to control the voltage quite well. So I've assumed here that the voltage has actually remained constant, which means that this would then be the final torque speed curve. And this actually correlates very well with the manufacturer's curve. If I could overlay this onto their data, it actually matched quite well. Okay, so that was the result of that machine. Okay, so just a quick discussion of results in brief. This was a lot of time and effort. I thought it was going to be a quick exercise, but this took months. The Spectrogram app, using a Spectrogram app worked surprisingly well. It took quite a lot of time to get familiar with it and to find an experimental procedure that worked. But once it was all set up, it actually worked very well. The testing environment was very challenging, as I think I've emphasized that already. The data points were manually chosen. I think in future we could extract data points much better than I could do it with my eye by using some image processing applications. And the curve fitting was done by trial and error. But what I suspect, and what would be a very nice topic for future research, is by investigating, if we knew some details about the rotor circuit, so if we knew that it was a double cage machine and the slot was deep or whatever, we could come up with some vague model of that, and we could immediately then constrain the order of the curves that we're going to put through at a later stage. That simplifies the whole problem, because it means you don't have to guess what order to use. How I got to the third and fourth order was by trial and error as well. I think I went up to the 15th order or something, but the lower orders work better. And I'm speculating that they're directly related to that rotor circuit. But I think that would be very interesting research in the future. Okay. It was very nice to differentiate that algebraic equation, because you have this perfect noise-free acceleration trace, which gives you a very nice torque speed curve. So that was a major benefit of doing the work. And I think the results were surprisingly good. There was very good correlation with the design data. And it was very easy just to walk in there, use my phone, and walk out again without carrying in loads of equipment. Okay, some recommendations. So to improve it, as I've alluded to already, I think the order is related to the rotor circuit, and that would be very interesting research, because if you know that, if you knew the rotor circuit, what you're expecting, you could use a gray box model which says, I've got a double cage machine, I'm expecting something like this, these are my data points, I can put them in and I can immediately make that process a lot easier. So using some kind of gray box model. Quite interesting research. Subsequent to this work, I thought it would be interesting to maybe put a parameter estimation element into this. So if we could, for example, the voltage measurement is still a problem, because if I had to test a larger machine today, I would have to probably go back and use an old method, because I need to know what's happening with that voltage, because it's critical. But if I could estimate what's happening to the voltage, possibly by measuring the current. So if I've got a electric model of the circuit, and I can measure the current going into it, which I could record quite easily, then I could work backwards to determine what the voltage was and use that. By estimating the voltage, I could then scale my curves without even interfacing to the control room to measure that voltage. But one of the weaknesses of this technique is harmonic torques. So here's a machine, very nice classic curve with a very evident harmonic torque, and that's obviously due to the stator rotor slot combinations. Just out of interest, this was a problematic machine to test, because the locked rotor torque, it was very hard to differentiate, is the harmonic torque on the left of zero speed, or is it on the right of zero speed, or is it at zero speed? So where do you put the locked rotor test value into this? Do you put it over here, do you put it over there, or do you put it over there? So this was an interesting machine. But I wouldn't be able to do this work with the method that I've just showed you. I think the data points were too few. In fact, you'd completely miss the harmonic torque. It would be undetected. However, I think if you knew the stator rotor slot combinations, you could include it in the model to say, right, got these rotor bars on these number of rotor bars, these number of stator slots. I'm expecting a problem at this frequency, and then you could change your order when you're doing the curve fitting to try and detect that. And I think that again would also be very interesting research. Okay, I was asked at the conference, can we use this for other machines? The short answer is not really, because in this case we are looking at asynchronous machines, so we are trying to determine torque versus slip effectively. However, you could use the audio processing to model a machine plus drive plus control loop. So you could give it a step response, measure the audiogram, extract the speed versus time trace, and you could then work out a system response to that. So the technique used here could be used, for other applications where you're looking at it at a system level. But if we're looking only at machines, specifically at machines, because we're dealing with an asynchronous machine, this obviously works. So you wouldn't be able to do this for a DC motor or a synchronous machine, obviously, because it's synchronous. So it wouldn't work there. Okay. So where do I see this going? If we can do some parameter estimation to try and estimate the voltage, or measure the voltage, or estimate the voltage, measure the current, we would know another variable, and then combining with the audiogram, we could eventually produce something that runs on a smartphone that could do this on site in location. So if you could disconnect the machine, run it at a reduced voltage, measure the audio, measure the current, you could then be able to produce a curve on the spot, is what I'm suggesting using the processing ability of these smartphones. And I think we're there. I mean, the apps are already very good, and the sampling frequencies are extremely high. What I didn't tell you is that audio trace was sampled by the phone at 96 kilohertz, which is much higher than the oscilloscope was doing it originally. So there's huge computational and signal processing ability in our pockets, and maybe that's where we go. Okay, just to conclude, so we were looking at torque speed curves for induction machines. And I'll show you the traditional method using a handheld tacho generator, which has been around for decades. Very simple. It has its problems, and hence we explored this new idea of using an audio spectrogram. The problem with it is that you can't get the data close to the zero speed where you really need it for the log rate of torque. So that brings in a need for some curve fitting to try and estimate, well, I've got this other data, what does it do there? Well, I don't have data. And it's not quite the end of my presentation, but what I'm suggesting is that with some grey box modeling, we could then, if we know some detail about the machine already, we can then accurately predict where the curves will fit the best maps through the data. And then finally, I must say special acknowledgements to Acton for allowing me to share this. Obviously there's a lot of information about the machines there, but we've been working with Acton for decades now, and this was a really interesting experiment, and they were very happy for us to do this kind of work. Okay, I see my things dying. Okay, I think that's basically the end of my presentation. I hope you enjoyed it. I hope you found it interesting. I hope I didn't go too far into the academic side of the mathematics side, and I'll try and answer any questions if you have any. Any questions? It's time to silence.
Sorry.
The problem the motions of machines on the
Yes.
but what you're seeing is getting closer to speed.
Yes.
Sometimes it'll actually over accelerate.
Yes.
It'll overspeed.
Yes.
And then come back to
Yes.
synchronous speed.
Yes.
Because of the acceleration that is
Yes.
being present, so it actually breaks that very last little bit.
Yes. That's quite interesting. In fact, with when you do the speed versus time, as you can actually see it does oscillate. That's overshoot slightly. Yes. Yeah. In fact, you wouldn't be able to pick that up because it's just the resolution is too low. Yeah. In this case, using a tacho generator, yes, you can sometimes see that.
They're all very nice polyphase power but I really think there's a kind of also speed everything at the same time. Very, very accurate. Yes, to do that.
Yes, yeah, that would be quite nice. Yeah. Especially if it's portable.
Oh, it's a lot of boxes.
In fact, in the background research, there's quite a lot of work looking at using the saliency of the machine to work on the speed versus time trace hidden in a current harmonic. So as a machine is rotating and the air gap is not uniform, it's obviously going to create other harmonics which are evident in the current waveform. And you can pull out the speed versus time trace from the current waveform and then do all of this. So instead of using an audio signal there, like what I've done, you could use a current signal, pull out a particular harmonic, which is due to the saliency.
Do the same thing with the polyphase power.
Yes.
Already the software is already there. It's done in much.
We can take some questions online.
Yes. Any questions?
So, is there any questions from the attendees online? You can just unmute yourself and ask your question. Thank you. Just said it it's a insightful presentation, lovely research outcome, well done.
Okay, yeah, perfect.
Very interesting.
Good. Okay, perfect. So do you have any questions?
So all work environments.
Yes.
All running.
Yes. Yes.
So the idea use some sort of solid conduction and use bone.
Yes, yes.
Will that then be the solution where something would fit onto your cell phone?
Yes.
Jane will create an app for me.
Yeah.
I go there, I hold it onto the casing. Press the button,
Yes,
and I get something.
that's right. Yeah, that's what I'm suggesting. Yes.
It's,
Yeah, you know, the problem is the audio channels bring sound from everywhere. If you put a direct conduction channel, the bulk of the sound source is obviously going to conduct through directly. Yes.
we're measuring sound, we can able to measure vibration and so.
Yes. Yes. Yeah. So you could, in fact, you could do this. That would probably be the first prize, is that if you could measure the vibration instead of the sound, then that immediately removes a lot of the noise environments. Yes. So vibration would be the first. I think that would be the first prize.
Just another comment. Controlling the voltage is also not so difficult to put a voltage controller on it.
Yes.
So you can control it very smoothly so that you don't have to do that much compensation for.
That's right. Yeah. Yeah. And on that note, obviously controlling the voltage for the smaller machines is much easier. And so when the machine becomes comparable to the generator set, it becomes quite a task. And in fact, very often you won't be able to do that constant. It will drop. You'll have to measure.
Yeah, so if you think that instrumentation can enhance the quality of analysis,
Yes,
like
for
the
sure.
pump station situation, with the vibration monitoring systems, smart transmitters, feeding into a SCADA system.
Yes.
Will that help?
I think that would help a lot because you've already got access to all of these measurements anyway. Now, the only problem really is one would have to decipher the source of vibration. Is it coming from the machine or is it coming from the load or something else? But it doesn't really matter because in this case, we're not really looking at the what that vibration is doing. You know, if it's we're not trying to identify a fault or anything like that. We're just trying to use it as a signal which is related to the rotation. So we could if we could establish what's causing the vibration or how's that vibration, that harmonic related to the speed, you know, it's an integer multiple, then we could use that as the speed trace. And we're looking at in this case, the acceleration of it. So we're not looking at what the harmonic is telling us. We're just looking at, can we measure that harmonic over time? And we'll differentiate that to work out an acceleration. Yes. So to answer your question, yes, I think a lot of the instrumentation probably is in place and you probably could use it. Yes.
The 500 kilowatt or half megawatt motor.
Yes.
What is the rate of voltage and what voltage did you do the test at? Because you said because it's a force saturation there, you do that.
That's a good.
You didn't have that on the slides.
Did I not put the voltage there? I think it's.
Next time missed it.
Just have looked it up with the voltage there.
I was
That's a
watching for that.
That's a very good question. No, I don't think I put the voltage there. It was in either 6 kV or maybe 11 kV. I'm not sure. And the test was done at 850 volts.
850.
Yeah.
So I think
Between 800 and 850 volts.
and I think it's come up before the conversation your voltage constant.
Yes.
You have a strong source.
Yes,
Still can't expect that much.
Okay.
If you've got a low source peaks
of course. Yes.
on the other end.
Yeah.
So that's not always possible.
That's quite right. Yeah. So in this environmental setup, it's powered by a synchronous generator sort of sitting next door on the test bed, which is in the order of megawatts, maybe 5 megawatts, and we're running at half a megawatt. So I was quite confident that we would be able to have a relatively good voltage regulation, very low impedance on the generator side. But if we had to do the test on a larger machine, I would be concerned.
No, then you have to have some form. That's what was you said earlier, to try and keep constant like
That's right.
that's what it citation control.
Yes.
That responds quickly.
Yes. That's quite
But
right.
then also the prime mover has to respond quickly too.
Yeah, it's quite right. So with the large generator, it's got very high inertia, so the speed is quite good. But it's just the voltage regulation, which in this case is done manually, controlling the field on the generator set.
Like you get to the generator, you get to that your rock rotor torque.
Yes.
You're going to be drawing quite a bit of power. And that prime mover has to respond quickly, otherwise you're not going to be the constant 50 hertz.
Yeah, that's quite right. Yeah. So that's, it would be to really define this, we would need to measure that voltage. Then there's no grey areas related to that. Yeah. So this machine, I didn't have that access for this small machine, but I wasn't too worried about it, you know, for the reasons discussed. Yeah.
Big one.
But the big one's important. Yeah.
It's another story, and but obviously then you have a set of meetings that you're gathering it.
That's great. And in fact, when Actom invite me back to do a bigger one, I'll compile a new presentation on how we solve that problem. Oops. I'll do it for that. And the next year we'll have.
Your talk is proportionally to the squares voltage.
Great.
So he's extremely marked. It's a marked. It's an exponential function.
That's correct. Quite correct.
How do you control the frequency? You said it's driven by a synchronous machine, but what drives the synchronous machine?
That's going into details. What have you got in it? A huge induction motor driving it. That's right.
So that would.
So it's not quite 50 hertz.
Yeah, it influences the frequency as well.
Of course. Any other questions?
Do you want to also identify the machine's parameter?
Possibly, yes. It might be when they do the verification tests, there's a whole battery of tests of which they're trying to identify other machine parameters. So it might be worth adding that functionality that you could, when you're doing tests, could extract that information as well and compare it to other test results. So that could be quite interesting and possible.
Good, thank you.
Good, thank you, everybody. I hope you learned yourselves a super afternoon.
Session after maybe 2 years, 2.5 years. Two-person session. So
Thank you.
And I also last week I did thank you for a time as well to get everything in. Thank you so much.
Thank you.
Okay.
Thank you, Mitch.
Just complete, thank you.
Thank you. Bye-bye, everybody. Thank you. Bye, Joanne. Bye, Gerald. Stop your recording, hoor.
Thank you. Bye.
Bye.